Okay, so in the last lecture, we left off just on the previous slide here, talking about Constexpr for functions. So we're going to be continuing along on this theme. And Constexpr for functions is a lot more complicated to understand than Constexpr for variables. There's a lot more kind of going on, so I need to say quite a bit more about it. So there's a few more examples than what I really want to go through or have time to go through, I guess, in the lecture. So I'm going to skip over a couple of them and just focus on ones that are maybe the more important in terms of priority order. So what I want to go through is an example of using a Constexpr function for computing integer powers of some real number. So we have this function called power_int. It takes a real number x to raise to an integer power n and computes this result just using an iterative algorithm, as you can see down below here. And it's a Constexpr function. And this is the reason why we want to look at it. And there's a few reasons for wanting to go through this example. One of them is to make some comments about common misunderstandings about Constexpr as it applies to functions. Also to talk about some issues with respect to when things are actually computed at compile time versus when they're not, versus when you're not really sure. Because there's the kind of, Constexpr functions are quite nuanced. There's a lot to talk about. Anyway, the first comment I want to make, though, is that, and this is a very common misunderstanding that at least a small number of students typically have, maybe it's even larger than I realize, or at least some students have this misunderstanding, which is that we have this Constexpr function here, therefore all the local variables inside this function should be Constexpr. No. In fact, most variables you probably don't ever want to make Constexpr. And in particular, in the common case, the most common case is probably most of the local variables inside a Constexpr function will not be Constexpr. So for example, if we look at this variable result, so if we look at what it's doing, it basically sets the result to 1, then it does some iteration, basically doing repeated multiplication and returns the result here. Why would we not want to make result Constexpr in this particular function?
You're modifying it.
Right. Well, yeah. So if we make a Constexpr, if I were to add Constexpr in front of double here to make this a Constexpr variable, the important thing to remember, Constexpr does two things. And some of the students who maybe get tripped up by this, they forget the second thing, the more important thing of what Constexpr does. The thing that typically people won't forget is Constexpr is basically forcing the variable to be computed at compile time. But there's another really, really, really important thing that Constexpr does, arguably the much more important thing, which is what? What effect does it? It doesn't just make the value computed at compile time. There's something special about the value. Yeah, you can't mutate it. At the instant that you create it, you must initialize it, and you can't change it thereafter. So the second part, it's not because of the first part that we wouldn't want to make this Constexpr. I mean, because we kind of do want this computation to happen at compile time. But the thing is, in order for this algorithm to work, it has to mutate the value of result internally inside that function. If we make it Constexpr, this implicitly makes the variable const, which means you can't change it. You initialize it, you can't change result, and we're always going to return 1 from this function. Well, actually, we'll get a compile error, but if it were to return a value, it'd always be returning 1 because we can't change it from 1. So important takeaway from this is not really the main point of this slide, but I just wanted to mention here because it's the first place where we actually have an example of a Constexpr function where there's some looping or some other things where we're actually mutating state inside the function. And in particular, we're mutating lots of stuff here. Like we're mutating the value of n here. We're like basically changing n in a loop. We're mutating the value of result, and so on. You can mutate lots. You can mutate any state you want inside a Constexpr function. To make a long story short, and we'll look at it in more detail later, the thing that you can't do is you can't have the computation that the function does depend on state that's external to the function, like global variables, other state that's only known at runtime. But these local variables, any local variable in a function is always known to that function and only known by that function. No other function can see it. So you're fine to change, mutate state inside a Constexpr function. And actually, probably most of the variables will not be Constexpr for this particular reason. Anyway, so getting to maybe the main point of the slide, at least at this point, we'll kind of come back and look at some of the nuanced aspects of Constexpr that I was alluding to in the first part of the slide a little bit later. The main point of this slide is really to illustrate the issue that I raised in the last lecture, which is that just because you make a function Constexpr, all Constexpr is saying is that this function, in principle, for some arguments that you could pass to it, it could be computed at compile time. It doesn't say it will be, it says it could be. It's just basically signaling to the compiler that there is some hope in heck that you could actually compute this at compile time, maybe. It doesn't say if you can do it, you have to do it. It just says maybe you can do it. it's kind of a signal to the compiler that maybe there's something I can do with this in terms of, basically optimization and doing stuff at compile time instead of runtime. Because of this, this raises the question, like, when do things actually happen? Like, what can we say about when computation actually happens? So what I have in the code example down below, this main function that's using the power_int function, it calls it 3 times, once here, and then once at the bottom. And what I want to comment on is what we can or can't say with regard to when that computation will happen. We're calling a Constexpr function. We know in principle, maybe it could be computed at compile time, but we don't really want to know maybe. What we want to know is, like, what can we really categorically say about this? So in the case of this first function call here, we can categorically say this must be computed at compile time. And the reason for this is that the arguments that are being passed to this function, namely 0.5 and 8, these are constant expressions. More specifically, they're, well, this is a double literal, and this is an int literal. Literals are basically constant expressions. You don't need to run a program to tell me what 0.5 is or what 8 is. Because the arguments being passed to this function are all constant expressions, and because this is a Constexpr function, in principle, the computer, or the compiler, I should say, could compute the result of this function at compile time. It could. Doesn't necessarily have to, except in this particular case, it has to. The reason why is that the result that we're computing here is being assigned to a Constexpr variable. The important thing on this line is we have a Constexpr here. So the reason why this basically forces the compiler's hand. If we weren't doing an assignment, if we were just calling power into it and we'd be throwing the value away, the compiler would not need to compute this at compile time. The reason that it could, because we can observe that this function could be computed at compile time with the particular arguments that we're passing here. But there's no requirement that the compiler has to do it unless we do something to force its hand. And in this case, we've done something to force the compiler's hand. What we've done is we said, let's take the return value from this function, which may or may not be computed at compile time, and let's assign it to something that must be computed at compile time. Because A is a Constexpr variable, it's required to be computed at compile time. So although the right-hand side of the equal sign here, in isolation by itself, does not need to be computed at compile time, it could be, but not required to be. As soon as we assign it to a Constexpr variable, it's now required to, because in order for the compiler to calculate A, which it must do at compile time, it must compute the right-hand side of the equal sign at compile time, and this forces the compiler's hand. So we can categorically say, in the case of this line here, power int must be called at compile time. There's no possibility of any other sort of behavior happening.
If the power int function didn't have the Constexpr label, is there still a chance the compiler could decide to compute it at runtime? Okay,
so if we left out this keyword here, then what we're saying is this is not a candidate for compile time execution. Therefore, if we tried to do this, what would happen? Likely, you'd probably get a message from the compiler saying, basically the right-hand side is not a constant expression. You're trying to initialize a constant expression, this variable here, A, with something that on the right-hand side is not. So the Constexpr is there. The compiler will not, unlike some other types of optimization, as far as I know, the compiler is not permitted to just say, oh, for fun, I'll just do this at compile time, even though you're not asking for it.
Is there any reason not to make like all of your pure functions Constexpr?
To make all what functions?
So all of your pure functions, should they all be Constexpr?
I mean, I guess how much of your code you want to make Constexpr really depends on how much maybe benefit there is from doing compile-time computation. There might be some things where maybe it's just not worth it. But for a lot of types of functions, like for something like this, I guess in a lot of cases, if you can do it, probably the inclination might be to do so if there was some reasonable expectation that maybe it might be callable at compile time, and the benefit of doing so would be deemed, beneficial. Because there's a downside, like, you can, and you'll see this when you do the programming assignment for this part of the course, where we're going to completely brutalize the compiler, doing really obnoxious levels of compile-time computation, probably much more than you would typically ever do in practice, mainly just to show you can do it, to demonstrate, because one of the things I want you to get out of this unit of the course is that the notion of compile-time computation is extremely powerful. You can really do a lot with it. And we're gonna do a lot with it. We're gonna, the poor compiler. But to make a long story short, what the point that I'm getting at here is that it's not really the poor compiler, it's poor you, because you have to wait for your compile to finish. And you're doing a lot of computation at compile time, it can really, really, really slow down your compiles. And because when the compiler is doing the code at compile time, it's not like it's running it, it's basically running it, it's doing an interpreter. Like the compiler has a built-in C++ interpreter that it runs. because basically it's interpreted, like it's going to be run much slower than if it actually ran as native code that you compiled and built. So if you start doing a lot of compile-time computation, it really slows down your compiles a lot. So this might be one reason that perhaps you might not want to start doing too much stuff at compile time if it wasn't felt that there would be a benefit to doing it. Because maybe there's some things that are a little bit slow, but they're only done once in your code, and maybe you just don't really want to be waiting for them to happen at compile time. Any other questions? Yeah?
Could that be selectively turned on or off when you compile it?
So like if you put Constexpr, then it's sort of up to the compiler what to do, unless you kind of force its hand. In some circumstances, like we saw, the compiler has no choice. We forced it to do it at compile time. But otherwise, it's kind of whatever the compiler feels like doing, if I understood your question correctly. Any other questions? Okay, well, let's go to the next function call that's made for powerInt. So the next line here, we have powerInt. It's being called with arguments that are both constant expressions. 0.5 and 8 are examples of constant expressions. So in principle, you could compute, do the computation that powerInt does at compile time, right? Because the only thing that the computation here is depending on effectively, like the only thing that this computation here depends on is what's the value of x and what's the value of n. So if I know what x and n are at compile time, like what their values are, I can do the whole computation of this function at compile time. This is maybe the easier way to think of it. I mean, the whole spirit of Constexpr is like, is there any state that you need that you don't have in order that you would need at compile time that you don't have access to? If the answer is yes, then you can't do this at compile time. In this case, though, if both of these are the values that are being passed in here are both constant expressions, so they're known at compile time, and because this function is such that basically all the computation, all the steps that are taken here just depend on the values of x and n, in principle, it could compute it at compile time. So in principle, the compiler could compute this right-hand side here at compile time. The question, though, becomes, well, does it? The answer is, well, the compiler is not required to. Again, compilers can be as lazy as they want with respect to Constexpr and Constexpr functions. If you have a function that's Constexpr like this and we use it in this particular way, the compiler can say, well, I'm assigning the result of this function to a variable that I don't have to compute at compile. Well, I'm not required to compute at compile time. It's computed at runtime. So I don't really need to compute this result at compile time. I could wait till runtime and then call this function and take the value and assign it to b. Alternatively, I could compute this at compile time and then just make at runtime it would just be a constant assignment. Like the value is pre-computed at compile time, and then this line at runtime would just look like b equal and then a number that's already been pre-computed. So there's kind of two options that could happen here. It entirely would depend on the compiler. It's left to the implementation, the compiler implementation of what to do. GCC tends to be fairly aggressive. The GCC compiler is fairly aggressive with respect to Constexpr. If it can, it generally tends to. Although I haven't looked at GCC 9.1, but at least in some of the earlier version, it tended to be fairly aggressive. Clang, I think, might be a little bit going the other way, although I don't use Clang as much, so I maybe can't really categorically say. But the bottom line is the standard doesn't make any requirements in this regard, whether the computation is done at compile time or runtime. And the main reason for this is just to give the compiler implementations leeway to make their life easier. The more prescriptive you become in a language standard to say, thou shalt do this, thou shalt do this, thou shalt do this, the more things there are that you shall do, the less people are going to want to implement the standard. Like it gets harder to do. And it also, for those, even for the people who are going to implement it anyway, it becomes more and more of a burden to do. Because in order for it to be compliant with the standard, there's more I's you have to dot and T's you have to cross to make sure things are compliant. So typically, language standards tend not to be overly prescriptive. Unless you really have to have a good reason to make them do something, you just say, well, whatever you want, do it, however you like. And this is the case here. Then we have a third function call to this power_int, this line here. In this case, we can categorically say there's no way that this function call could be evaluated at compile time. The reason in this case is if we look at what's being passed as the arguments here, well, 2 is a constant expression, so that's not a problem. But the argument x that's being passed here, if we look at where x is coming from, x is not a Constexpr variable. Basically, its value is going to be set at runtime. And to make it even more obvious, it's set at runtime. It's like we're reading it from the standard input stream. Well, how could you ever know what's going to be in the standard input stream at compile time? You don't know until the program runs it, because at least for any reasonable operating system environment, you can basically redirect from various different sources what the standard input stream is. So you don't know even if you're going to read a file. It could be reading from a network connection, whatever. So the bottom line is we have no idea what x is until we run the program. Therefore, if you kind of stop and ask yourself the question, could we do the computation associated with this function at compile time, given that we know what n is at compile time, but we don't know what x is at compile time, well, the answer is no, we couldn't do this computation, right? If we don't know what x is, we can't do this computation. So we can categorically say this last function call down here will be done at compile time. So kind of the moral of the story here is that if you want something to be done at compile time, basically what you do is you assign it to a Constexpr variable. Because otherwise you're kind of relying on the compiler not to be lazy, and it goes, well, I could do this at compile time, I'm going to do it. But this would be a mistake because the language standard allows compilers to be as lazy as they like with respect to Constexpr. So unless you force them to do it, they won't necessarily do it. And if you want to make sure that across all, if you're doing like multi-platform development and maybe using multiple compilers, multiple versions of compilers, and you want to make sure on all the platforms with all the compilers you use, something is evaluated at compile time, then you have to do this. You can't rely on the fact that, well, maybe I'm using GCC, things will be okay. I'm using another compiler, well, I just kind of pray. But ultimately, one of them won't do it, Murphy's Law. And I think that's all I want to say about this slide. Any questions before we go on? So why might we want to do compile time computation versus runtime computation? I've tried to list on this slide some of the benefits. I mean, some of them are maybe more evident than others. Perhaps the most evident one is the first one that's listed here. I mean, the benefit of doing things at compile time is there's no runtime costs. Like you basically completely eliminate the need for any CPU instructions to happen at runtime to actually do some computation. But that's not the end of the story. There can be quite a few other benefits as well, which I've listed here. So this might facilitate other compiler optimizations. Like for example, if the compiler knows something about results at compile time because it's doing some partial part of the computation at compile time, this might facilitate other optimizations that might not otherwise have been possible. So in some cases, it might help the optimizer, possibly. Another benefit that kind of is self-evident once you think about it, but you might not stop to think about it at first, because usually people care about speed of code, but they don't go, well, how big is my code? Another benefit of Constexpr code, if something happens at compile time, and it only happens at compile time, in other words, the function is never called at runtime, there's no reason to actually ever include the CPU instructions for that function in your actual program, because those instructions would never run even if they were there. So it can potentially reduce code size. So maybe in some situations where you're very constrained for memory, maybe some embedded systems, maybe this could be somewhat of an issue. Another benefit is that you find errors at compile time. So like if something goes wrong in terms of, like there's lots of things that can go wrong with Constexpr functions, as you'll find out. Some of those things would be indicative of bugs, and you will catch them at compile time, because as the compiler is trying to basically interpret things at compile time, it goes, hey, this doesn't really make sense. You have undefined behavior here. This is invalid code. So you find out about things at compile time rather than link time or runtime, and this helps to save problems. And generally, the earlier you find the errors, the better it is. You can fix things more easily. Some other things that are kind of getting into more gross sorts of problems. There's always this issue about order of initialization. If you have a bunch of, for example, global variables in your program that are not like Constexpr, for example, so they're initialized at runtime, then you have, well, what's the order in which they're initialized? And if some global variables, their initialization depends on other global variables, then the order matters. And then the question becomes, well, what order is my global state or static variables as well as sort of the same issue? What's the order in which things are initialized? And you have to be very careful. If things are not initialized in the right order, then your code breaks. Unfortunately, the language standard doesn't make too many guarantees about the order in which global variables, for example, are initialized. So this gets rid of all these problems because things are computed at compile time. So you don't have to worry, well, what's the order things happen at runtime? Well, it's initialized at compile time. It's not a problem. Another issue that can be sort of sidestep are synchronization sort of issues. So if you're doing like multi-threaded programming, all the problems about like data races and stuff kind of goes away, like synchronization that might be required when you're trying to initialize objects, because basically the compiler is doing it at compile time. There's not multiple threads of yours that could basically cause data races. So there's like quite a few different benefits potentially that can come from compile time computation. Probably for most people, the most exciting one is the first one, that you can save execution time, but there's other benefits as well. The last bullet on this slide is just making some comments that to kind of point out that there can be some subtle differences between if you compute things at compile time versus you compute things at runtime. In other words, you might get slightly different results, particularly if you're using floating point arithmetic. Because the floating point arithmetic is computed by the compiler, right? The floating point arithmetic, when you run your program, is being computed by your program. On some systems, or like some develops for some development environments, these are not the same system. In other words, you build on one system architecture, you run another when you're cross-compiling. I don't know if any of you have done stuff with embedded systems and so on, but you have their tool chain on maybe typically some Unix host, maybe, or maybe Windows. And then when you build the code, then you download it to the embedded platform and run it there. Like, they're not even the same machines, don't even have the same CPUs. So unless the compiler does fancy things to make sure it does the floating point arithmetic exactly in the same way that the target system is you're building for, you can get slightly different results. I don't, to the best of my knowledge, there's not anything in the language standard that requires them to be exactly the same. So there's some latitude allowed. Of course, things have to be within reason. You can't have like massively bad round off error when you're doing things at compile time. It has to compute the right result. But you may get slightly different results because you may be using actually different processors potentially. Also, rounding modes. Rounding modes are an issue too, because when you're doing floating point arithmetic, you can also set rounding modes, like round towards 0, round towards minus infinity, round towards positive infinity, and so on. These things can be changed at runtime. To the best of my knowledge, at compile time, it's just fixed. You can't change. So you can get subtle differences between the two. But typically, this is not a big problem, but I just want to point out that you can have some slight differences. So with that said, I want to kind of go and look at things from the class point of view. So far, we've been kind of just focusing on kind of regular, like non-member functions, but you can also apply Constexpr to member functions as well. And basically, a lot of the semantics is sort of similar. Because Constexpr, like member functions can have other things, like they can be virtual. Then there's other issues that arise, like can you have virtual Constexpr functions and so on. You can't, as it's kind of noted on the slide here. So there's some additional restrictions that are imposed beyond sort of regular functions. When you're talking about member functions, in addition to all the rules about what you can and can't do for regular functions, and with Constexpr, there's also some additional restrictions that are imposed, and I'll talk about some of these things a bit later. I think I already touched on this point here on the second last bullet. Constexpr member functions are implicitly inline. Basically, it's just if you wrote the inline keyword in front of them. But they're not implicitly const. So this is a very big difference between like Constexpr variables versus Constexpr functions. With Constexpr variables, when you say Constexpr, that thing is implicitly const. Once you initialize it, you cannot change it because it's implicitly const. For functions, particularly member functions, one does not imply the other. I mean, Constexpr, you can have a Constexpr member function that is or isn't a const member function, for reasons that I'll talk about in a moment. Well, they actually got this wrong. This is why it says as of C++ 17. I believe actually in C++ 11, where this feature was introduced in the language, they made Constexpr imply const for member functions, and then they realized after the fact, oops, this is a mistake, because there's lots of reasonable things you'd want to do that we can't do. So anyway, but I only teach, this is one of the luxuries of teaching at university. There is no such thing as legacy code. C++ never existed before C++ 17. So basically everything I'm teaching you in this course is with respect to C++ 17. If you go to older versions of the language standard, good luck with that. Lots of things are probably going to be different. Other things won't even be there at all. Anyway, hopefully you won't have to deal too much with legacy code when you go out into industry, but some of you inevitably will. There's a lot of it out there. You probably have to face it at some point. But if you can avoid it, probably it's preferable to do so. We can also apply Constexpr to constructors for classes. And there are certain constraints that are placed on things. I mean, basically, maybe I should point out, like both for member functions as well as constructors as well. Like constructors technically aren't functions in terms of standard use, but I think it's best to think of them just like a function. But technically, I understand that they're not really, strictly speaking, a function. But for our purposes, as mere mortals and not compiler writers, they pretty much look like functions. Anyway, they basically, the idea is the same. Like as long as the arguments to the constructor or member function are all constant expressions, then you can kind of guarantee that or at least in principle, you could do the computation associated with that function at compile time. And I think this bullet might be new. I think I added one bullet on one of these slides compared to what you have. It's not a really big deal. It's just pointing out that there's additional restrictions on constructors. If you have like a regular constructor versus like non-Constexpr one versus one that's Constexpr, there's things that you can't do once you make it Constexpr. Like generally making things into Constexpr functions or constructors, it puts in more limitations on what you can do, which makes sense, right? Because it's certain things you know that you couldn't do at compile time. So the language just steps in and says, I'm not even going to try to let you be insane. I'm just going to say you can't do this. And the compiler will look in error. And just like with all regular like member functions, a Constexpr constructor is implicitly inline. So let's look at a little bit more fancy examples. So this is an example of a simple two-dimensional vector class. So we basically have a pair of real numbers, which are represented by doubles here, the x and y component of the vector. And then we provide some very basic sort of operations that we can perform on the vector. We can default construct it, and it just initializes the vector to 0, 0. What else can we do here? We can construct it with an x and y value. We can copy construct it. We can copy assign it. We can get the x value, get the y value, get the square of the norm, like the squared length of the vector. The reason for returning the squared norm is just to avoid the square root nastiness. We don't have to compute the square root this way. It's a lot of algorithms. They don't need the square root. The squared norm is good enough. So anyway, in case you're wondering why there's no square root in there. This is not an uncommon thing to see in geometry processing, for example. Anyway, so we have a few Constexprs, well, actually quite a few sprinkled throughout the code here. So we have like a Constexpr constructor, another Constexpr constructor. We have some other kind of non-constructor type member functions that are Constexpr as well. I mean, pretty much everything is Constexpr. And then down at the bottom here, we have some code that's actually exercising the class up above, and we have some Constexpr variables here as well. And by the way, I don't know if are people familiar with static underscore assert? I mean, I think probably everyone's familiar with assert, especially if you used C before. The only difference between static assert and assert, essentially, is that static assert is a compile time assertion. Like the condition, the thing in the brackets here has to be something that's known at compile time, a constant expression. It just allows you to assert, but at compile time rather than runtime. Because if you use the assert macro, that's tested when your program runs. There's no way to make it tested when the program's compiling. So in cases where you want to test something at compile time, you can use static assert. Yeah. There's also an optional string that you can put as a second argument that if it fails, it prints that error message. But I'd say it's maybe of more limited use. What do I want to say about this example? Well, you can see that pretty much everything is marked Constexpr. And so, for example, we can do something like this. We can create this vector v with the values 3 and 4, which is going to invoke the second constructor up above this one here. Because this constructor is a Constexpr constructor, this is saying, in principle, this object, this could be used to construct an object at compile time. Because we can actually construct this object using this particular constructor at compile time, it's valid to put Constexpr in front of the vector here. So in other words, this actually can legitimately be created at compile time. And because we're making this a Constexpr variable, we're forcing the construction to happen at compile time. The object's actually being initialized at compile time. And just to kind of test the basic sanity of the code, I'm asserting that v.x is 3 and v.y is 4. In other words, I'm checking to make sure the vector after I created it really did have 3 as the x coordinate and 4 as the y coordinate. And this test, again, is being done at compile time. If this fails to be true, it will be flagged at compile time, not at runtime. Whereas if you made this an assert, then it would be doing the check. It would still work, but it would be doing the check at runtime, which is probably not really what you want, because this is actually checkable at compile time. Again, prefer checking things at compile time rather than runtime. Prefer checking things at runtime or at link time rather than at runtime, and so on. Earlier is better for finding mistakes. Then we have this line here where we're taking our Constexpr variable v and we're computing the squared norm of it. So it's going to basically invoke this member function here. This member function here is a Constexpr member function. So in principle, it could be computed at compile time. Because we're taking the return value of this Constexpr function and we're assigning it to a Constexpr variable, this forces the compiler's hand. It must compute squared norm at compile time, because otherwise it couldn't initialize the value of this Constexpr variable at compile time, which it's required to do. So again, the common pattern that you'll see is if you want to force something to happen at compile time, assign it to a Constexpr variable, and this will force it to have to happen at compile time.
If you want to assert that will run at both compile time and runtime if necessary, so a Constexpr function that could be called either compile or at runtime, is there like a solution for that, or do we have to double up on all of our asserts?
I think I'm not quite sure if I understand what you're saying. I think I understand what you're saying. I mean, I think probably in most practical cases, you would probably know whether the expression that you're dealing with is a constant expression or not. Like most typically, you wouldn't static assert and assert. Either you would recognize something as being a constant expression and say, I'm going to static assert that because I know it's a constant expression and I computed at compile time. Or you would say, no, I don't know necessarily that that's going to be computed at compile time. It's not a constant expression, therefore I'll use assert. But most typically you would know, I would say probably in a lot of cases, majority of cases, you would probably know which is the case. But the preference would be, if it is a constant expression, it'd probably be preferable to use static assert, because that way if something went wrong, like the assertion fails, it gets flagged at compile time rather than when you're running the program. So you find out earlier. Again, it's better to find errors earlier rather than later.
As meant in the context of this, where we have this object which could be used at both, like we could either compute it entirely at compile time, or it could also be used at runtime. We may have cases where we want to check, assert something both at compile time and runtime.
Yeah, but the thing is, what I'm saying is, like when we invoke, like when we're invoking these functions down below, we can look at what parameters are being passed, and we can say this is a constant expression, it's being computed at compile time, therefore we want to use static assert. Like, I mean, there might be some, I'm not saying that there's not some situations that could, like, it's probably possible that there could be situations arise where you're not really sure what's happening, like is it happening at compile time or not, like, but you should still be able to tell whether something's a constant expression. So if it's a constant expression, use static assert, otherwise use assert. Yeah. Any other questions? Okay. Anything else I want to say about this slide? Maybe this is the last comment. Like essentially, all the computation associated with lines 22 through 24, they're all done at compile time. So essentially, the CPU instructions that will be generated for this code is something like whatever the result of D is. I guess D is going to be like, is it 3 squared plus 4 squared, I guess. 25, something like that. Anyway, it's going to just print out the result that was computed for the squared norm. So like there's not actually any computation happening. It's just a matter of there's some constant that's been computed at compile time, and simply at runtime it's printing it out. So there's not really much computation that's happening here. It's essentially just doing the computation associated with outputting stuff to a stream. This is just giving a little bit more detail with respect to a comment that I made earlier, which is that unlike the case of Constexpr variables, where when you say Constexpr, it implies const, it's a different story for Constexpr functions. So like if you're talking about member functions, const member functions versus non-const member functions, if you say Constexpr, it doesn't imply the member function is const. And the reason why is, I just picked a relatively simple example to try to illustrate why you wouldn't want this to be so. And if you kind of wonder, well, why would you want to do this? Don't feel too bad, because again, if I recall correctly, they got this wrong in the standard, and then they had to kind of change it later. But you might want to do something like this. Here we have this widget type. Who knows what it does? It doesn't really matter. There's lots of like ... here, because a lot of the code doesn't really matter. But the basic idea is we have some way to construct the object at compile time, because there's at least one constructor that's Constexpr. If you don't have any Constexpr constructors, well, you can't use that object type at compile time because you can't construct it at compile time. You can't construct it at compile time. There's nothing you can do with it at compile time. The Constexpr constructor here, and then we have like an overloaded member function called get, which basically this type just stores, stores some integer value into it. This data member here, I underscore, and we can get the value. But we have two getters, like two get functions that we can use to get the value. And the only difference between them is we're overloading on const. This is a const member function, so the reference that's returned by this get member, it's a reference to an integer that's const. It can't be used to change the value that's returned. Whereas this one here, it just returns a plain int ref. So like a reference to something that's not const, so we're allowed to change the value that's the reference that's returned. So for example, and if, for example, Constexpr implied const, in other words, if the fact that we had a Constexpr here implied that this was a const member function, then automatically the compiler would place a const here where the cursor is, the mouse is, and we would have no control over it. Then what we would have is a compiler error, because we would have the same function defined twice. We would have like the const member function get, which is above, and then if it implicitly put const here as well, both basically the two functions are the same. It's a redefinition of the function. So this wouldn't be permitted. However, this is actually a reasonable thing to want to do, and sort of a very simple use case is something like what we have here, where we're creating a Constexpr widget called W, and then I just have a static assert just to show you that really the code is working. So it's asserting that the value that you get is 42, and this is going to invoke the const member function. It's going to invoke the first of these two member functions here. The reason why is that W is a Constexpr variable. So Constexpr for variables implies const. So this is a const variable, W. So when it's, because this member function get is overloaded on constness, the compiler will choose the one that matches in constness. So since W is const, it's going to invoke the const member function. So this is why it's going to, why this comment here says it's invoking the const member function, the const version of get. So far so good, but you might also want to do something like this. So here we're creating a widget, then we're getting its value, like this is going to be like a temporary object. It creates a temporary object, a widget, which is a temporary object. It gets the value, it returns a reference to it, and then we increment that value. And then we want to take that incremented value and assign it to I, which is a Constexpr variable. So at compile time, we want to create this temporary widget, increase the I underscore data member, and then take that I incremented value and then assign it to this Constexpr variable I. It's not an unreasonable thing to do. I mean, this is like a very contrived example in the sense that it's very, you know, what's the widget? I don't know. But you could imagine that this could very realistically occur in some real world code. I just made it like a kind of simple example so it fits on a slide and I can talk about it relatively quickly. But this is not an unreasonable thing to want to do. But this requires us to be able to overload on the constness for the get member function, because we couldn't increment this thing that's being returned here if the member function was a const member function, because then we couldn't change this widget because it's const. We couldn't return the widget dot get, the integer that's being, a reference is being returned to, because it would be const. Because up above here, if we only had this first function here, it's the reference that's returned is a reference to a constant integer, so we can't change the return value. Whereas here we want to change it, and it's not unreasonable to want to change it. Like it's just some temporary object, why shouldn't we be able to change it? And then just to show that the code's working below, I have a static assert to show that in fact the value that I is initialized is 43. The reason it's 43 is when we construct this temporary object widget, we're initializing I to 42, and then when we're returning a reference to that value, and then we're incrementing that value. So we're incrementing from 42 to 43. And then that's what I is getting initialized to. It's getting initialized to 43. Any questions? So like this is just meant as to show you kind of a simple example where you might want to overload on a member function with respect to constness, but you don't necessarily want the constness to kind of carry over from Constexpr, for Constexpr to automatically imply that the member function that's involved is const. Originally, the language standard did this, I think it was C++ 11, and then they changed this, I think, in C++ 14. Anyway, okay, enough about that then, since there's no questions. So before I can start digging a little bit more into Constexpr functions and so on, I need to talk about what are called literal types, because a lot of what you can and can't do with Constexpr functions and Constexpr code pertains to something referred to as literal types. It's just kind of a type that satisfies certain conditions effectively. It's called a literal type. And there's like a relatively, well, somewhat long list of properties that are listed here. But the main ones are really the ones that I've marked by stars. But I'll just kind of quickly go through this. If you have a type in the language that satisfies the properties that are listed here, so either it's void or it's a scalar type. Scalar type includes like integral types like int, long int, so on, and floating point types like float, double. Any pointer types, enumeration types like enums, pointers to members, which we'll talk about later in the course, but I don't expect probably anyone knows what they are because they're not used that frequently. Any kind of reference type or a class type, and probably for the purposes of this discussion, this is the part we're most interested in. We have some class type, so it's like a user-defined type, and then it satisfies these properties. It has a trivial destructor. Effectively, what trivial destructor means is the destructor doesn't do anything. Like you literally do not need to generate any code to destroy the object. In fact, this is what happens. The compiler does not generate any code if there's a trivial destructor. Which is, and essentially, like a lot of constraints that are placed on what you can and can't do with respect to Constexpr, a lot of the time it will say something like, you can only do this if the type is a literal type. And the reason why is if things aren't a literal type, for example, if they don't have a trivial destructor, you start to run into problems with respect to CompileTime computation. Like, for example, imagine that you had a user-defined type where the constructor allocates some memory using heap or something like that. Well, in a destructor, you're going to have to free the memory, right? Otherwise, you have a resource leak. But how's that going to work? Because let's see, we're going to try to run that code at compile time. So we're going to allocate the memory inside the compiler. It's like our program's not running then, right? It's the compiler that's running. So if we allocate memory inside the compiler, it's the compiler allocating memory, not our program. So we're going to like allocate memory inside the compiler. Then the compiler finishes, that memory is freed. It was allocated, it's not there, it's gone. The whole address space of the compiler is gone when it finishes compiling. And then when our program runs, we need to destroy the object at the end of the program, but now we're going to try to destroy a pointer, but the pointer referred to memory that was allocated inside the address space of the compiler when it was running. Not really sure quite how that's going to work, right? Like they're two totally different address spaces, so like this is going to have some sort of problems unless you do some kind of magic. In C++20, I think they've actually done some magic to make things work in some cases, but you can imagine how there can be problems, right? Because you're running the code at compile time in a completely different environment, an entirely different address space. It's the address space of the compiler versus what's happening at runtime. So when you start doing things with memory, like pointers and so on, you start to get into problems because pointers inside when you're running at compile time are pointing to stuff in an entirely different address space from the pointers at runtime. So if you start kind of mixing and matching them, you're going to get into problems because it's like comparing apples and oranges. They're completely different things. Anyway, so this is kind of on the, if you dig in more in terms of why do we have this constraint for having a trivial destructor, it's sort of like this sort of thing. If you're allocating resources in the constructor, you then therefore will need to free them in the destructor, but then there gets to be issues. The resource was allocated to compile time in a completely different process from the place where you're trying to free it, and this is most likely going to cause problems for almost any resource that you could imagine, whether it be mutex is being acquired and released or memories being allocated and freed. You're going to probably have problems if this is being done in entirely different processes with entirely different sets of resources and address spaces and so on. Anyway, so that's kind of making a long story out of a short point on the slide. That's kind of what this point's getting at here. So we need to have a trivial destructor, which is basically the destructor effectively saying the destructor doesn't need to do anything and the compiler doesn't need to generate any code for it. The next bullet here, the type needs to have at least one Constexpr constructor. If you stop and think about it, if I'm going to do something with a type, if I have a user-defined type and I want to do stuff with it at compile time, what's the very first thing you're going to need to do? Well, if you're going to do something with an object, you have to create it first, right? So if you don't have any constructors that are Constexpr, you can't create that object at compile time. If you can't create it at compile time, you can't do anything with it at compile time. And this is, again, the significance of literal types, as we'll see, a lot of it pertains to like what types can you do stuff with in Constexpr code. This is why you have this sort of restriction that you need to have at least one Constexpr constructor. The last item here in this sublist here is that all of the non-static data members, in other words, the ones that exist on a per object basis, because you can also have data members that there's only one copy for the entire class, what's called a static data member. Non-static data members are the ones where there's actually one in each object. The non-static is the more common case. Most of your data members tend to be non-static. And any base classes, if you're using inheritance, all of these things have to be literal types. The non-volatile, I would say maybe don't worry too much about that because it's unlikely you're going to use the volatile keyword ever in this course, and maybe ever in C++. They're even contemplating, I think, trying to slowly like get it out of the language because it doesn't really do anything except make a lot of messes out of other things. Anyway, so but for the purpose of this course, you don't need to worry about volatile. Volatile is another qualifier like const that you can attach to things, which generally makes a mess of the language in a number of different ways. The last kind of thing that can be a literal type is any array of literal type. And so I have listed some examples of literal types like int, double, an array of doubles, for example, double 16. Std complex is also an example of literal type. If you dig into the properties that that particular class has in the standard library, it's such that it meets the requirements of a literal type. An example of something that's not a literal type, well, things that do memory allocation, at least as the standard is currently specified in C++17. This may change in C++20, but at least in C++17, basically things that do memory allocation are pretty much not going to be Constexpr, because if you do allocation in the constructor, you're going to need to free things in the destructor, which means it can't have a trivial destructor, which means it can't satisfy the literal type constraint. Anyway, so a vector obviously needs to allocate memory sometimes because you need to store data somewhere inside the vector, and strings are the same. Strings are basically dynamically allocating space for the characters in the actual string. So these are examples of types that aren't literal types. And the last bullet, again, is the point of talking about literal types. It turns out that a lot of what you can and can't do is with respect to literal types. Like it will say, if you're going to be able to do this at compile time, then this thing has to be a literal type. Literal types, in some sense, are like simpler types. They can't do too many fancy things. Things that would cause problems with respect to compile time computation. So just to give some examples of things that are and aren't literal types, I have some examples on this particular slide here. So the first class that we have here, widget, this is an example of a literal type. The reason why, it has at least, for example, it has at least one Constexpr constructor, so that's good. There's some hope that we could construct one of these objects at compile time, which is kind of necessary if you want to use it at compile time. We have a trivial destructor. You may or may not be familiar with this notation here, but you can explicitly say, I want to default this to the compiler-generated default destructor. That if you don't provide a destructor, there's a certain well-defined behavior that it needs to have. So we're just saying explicitly we want to use that. If we could also maybe just not put it in, but anyway, this is an example of a trivial destructor, just basically using the one that the compiler would generate for us. So this is a literal type. It satisfies all the requirements. The data members are also, I believe, the data members, actually, I don't need to talk about that, I guess. This gadget is an example of a type that's not a literal type. The problem here is it doesn't have a trivial destructor. I mean, although we wrote the destructor ourselves and there's empty brace brackets there, meaning that we're not writing any code to do anything, the language does not deem this to be trivial. Trivial means you don't even say anything about what it does. Like you can say equals default, but thou shalt not write anything in terms of what the code should be, including an empty pair of brace brackets. As soon as you do that, it's not considered, this is just the way the language defines things. You could say, well, why? It's just the way it is. But anyway, if you do anything other than say equals default, like if you actually try to provide an empty body for the destructor, it's not a trivial destructor anymore. So this would violate the literal type constraint because of the destructor here. The last type here is another example of a type that's not a literal type. In this particular case, we have no Constexpr constructor. We have a constructor for this type, one of them, but the constructor is not a Constexpr constructor. So essentially, we have no way that we could actually create one of these two objects at compile time. Because in order to create the object, you need a constructor. And none of the constructors can be run at compile time. Therefore, we can categorically say there's no hope of ever creating one of these objects at compile time. Yeah. Any questions about any of these examples? Constexpr Variable Requirements. So we talked about Constexpr variables earlier, but now that we've introduced the notion of literal types and so on, I want to be a little bit more precise about what we can and can't do with respect to Constexpr variables. You can't just go necessarily making anything Constexpr you feel like. If you make a variable Constexpr, there's certain requirements that need to be satisfied. And of these three, typically, if you're going to go wrong, at least my experience in terms of the code that students write in this course, it tends to be the first two where things go wrong. The first is the variable that you're trying to make Constexpr must be a literal type. If it's not a literal type, it will be a compiler. You're not allowed to create one of these objects as a Constexpr object. It also needs to be initialized immediately, and I'm sure that this is going to bite some of you, at least to begin with. If you create a Constexpr variable, it must be initialized, which should, like on the line where you create it, which should make sense, right? Because Constexpr for a variable implies const, the instant that you create that variable, you can never change it once it's been created. So if you don't initialize it when you create it, you just created something with random garbage value that you can never change, which is not going to be useful in any application. So for this reason, the language forbids it. So you have to immediately initialize any variable that's Constexpr. And then this last part is basically the thing that you're using to initialize the Constexpr variable has to be a constant expression. It has to be something that can be computed at compile time. This tends not to cause problems as much for students because it's kind of self-evident, right? If you're assigning a variable, you're trying to create a variable at compile time, have its value set at compile time, obviously the value you're giving it must be something that you can compute at compile time. So the last bullet there is typically not so much the problem. The first one is maybe the most likely one to kind of more persistently bite you. But the second one will probably at first, until you get into the habit of initializing things, you might forget to set some things to be Constexpr, or sorry, to be initialized when they're Constexpr. And I guess I better stop here, otherwise I'm going to run over time. Any last questions?